Hello friends, welcome back to our channel Mirror Neuron, which means watch and learn. And today I'm going to share with you few of the basic questions that is commonly asked in neural networks. So the first question is related to the Tonnage function. I'll write it here, the Tonnage function. And the question typically will be asked is that the tonnage activation, typically works better than the sigmoid function when it is used as an activation function for the hidden units. And so tell me, is it a good idea to use a tonnage function instead of a sigmoid function? That is the first question. And also, why do you think that the tonnage function should be used as a activation function in the output layer? So first, let's see this. So the tonnage function looks somewhat like this, right? And this is -1 and this is 1, correct? So this typically would continue to be almost like a 0, and this is 0 somewhere. And the sigmoid function looks something like this, right? So this is 0.5 where it intersects with the vertical axis, and this close to 0, and this close to goes to 1, and this close to 0. Okay, so I will repeat the question again. The tonnage activation usually works better than the sigmoid activation function for hidden units, and the mean of its output is closer to 0, and that is why the data that the next layer will gets better, and that is why we use the tonnage function, okay, because the mean here becomes 0. Okay, so that is the first question that you might get. What is the difference between using a tonnage or the sigmoid function, and which would you prefer? But typically, if it is a binary classification, you might also use this one. So I would encourage you to read about both the activation function and when are they used. Okay, what is the second question? The second question is again related to know something as matrix factorization, or I can also call it as vectorization. Now, why these are important is because these are, you can say, the efficient methods to compute our, in deep learning, we are going to use millions and millions of records, and we want fast and better methods to solve those problems in a computer, right? So we need to, should understand how this vectorization and vectorized implementation are done. So typically you will be asked, like, say in a forward propagation, I'm pretty sure you're familiar with forward propagation, right? And in the forward propagation, say I have a neural network with L layers, okay? So in that case, how would you represent the output? How do you represent the output of a particular layer, right? So typically how you're supposed to explain is more of a vector notation or like a matrix notation. So we know that Z is used as a output of a certain layer L, and this is given by, and which is equal to the weight matrix W, and this will be for the layer, the current layer. But we know that typically the output, the input is from the previous layer. So again, we represent the input A with L minus 1 because we are getting the input from the previous layer, and in the first layer this will actually be X, right? Because this is the actual input in the case of layer 1. But because we are trying to generalize for L layers, so we'll write it L minus 1 plus the bias term, and which will be again from the current layer. Okay, so this is for the output, and for the activation, which is again given by the superscript L, and this will be equal to the activation function of that particular layer given by this. So basically this input gets in here. Okay, so this is how you're supposed to answer the question when we are talking about vectorized notation. Okay, so let's look into the few more questions. Okay, so question 3 is, suppose you are building a neural network and you are required to initialize the weights and the biases, right? So weight and biases. So what will you, start with? Should you initialize all of them to be 0? So should W be a 0, 0, 0, 0, and so on, and B also should be like a 0, 0, 0, and so on. Should you initialize all the values with 0? And if not, then what do you think would be the problem if we initialize them with all zeros? So the answer is, each neuron, in the hidden layers, or even in the first hidden layers. So these are your inputs. Say for example, these are your inputs, and these are your hidden layers, right? I will write it HL, and you could have multiple hidden layers, hidden layer 2, hidden layer 1, and so on. And finally, you will have some output layers, right? And these are all connected. I'll just randomly draw all these lines, okay? And then finally, okay, these are all hidden layers. So what happens is, when you initialize all of them with zeros, then each of these neurons, these are the neurons, I'll just bold it, okay? So each neuron basically will do the same computation. And we know that in gradient descent we do multiple iterations of the same calculation, but in this case, even after multiple iterations of the gradient descent, each neuron in the layer, so this is one layer, each neuron in the layer will be computing the same thing as the other neuron. So all of this neuron basically will be doing the same calculation. As a result, we are not going to learn anything new, and that is why it's a bad idea to initialize the weights. You probably could initialize with a bias of 0. That is fine to an extent, but you should not initialize the weights with 0, and I just explained why. Okay, let's look at a few more questions. Okay, so another question is, suppose you are building a neural network, and for all the hidden units, you are using the Tonnage as an activation function. And we have already seen in our first question what a Tonnage activation function is. And suppose you are using a Tonnage activation for all the hidden units, and now you initialize the weights to relatively very large values. So if I take an example, say you are initializing using a NumPy function, random dot rand n, and some shape of the matrix you are passing times say 5000. So you are initializing it with a very large value. So in this case, what are the challenges are you going to face? Okay, so that will be the question typically. So your answer is, what happens is, because the inputs of the tonnage is going to be very large, right, because of this multiplication. So this will cause the gradients to be very close to 0. Now you know already why the gradients will be close to 0, because if your graph looks something like this, and if your values are very high, so your z is going to be very high. Why? Because z is related to w like this, right? So if your w is high, your z is going to be very high. So what happens is, this value will be going to be very high, and as a result you can see this slope is nearly 0, not exactly 0, but very close to 0. And you understand the slope, right? That means if I move little bit by x, I don't change much in the y-axis. Okay, that is the definition of slope. So if you see here, the gradient is very close to 0, and as a result, the optimization algorithm will take much more longer to get to 0 directly, and hence it will become very slow. You get the point, right? So when your weights are very high, if you initialize with very high values, your z becomes very high. When your z is very high, your tonnage function is going to be very high, and as a result your gradient descent is going to be very slow, and as a result your optimization algorithm, which is nothing but the gradient descent, is going to be very slow. And that is the reason why we should be very particular about how we are going to initialize this value. There is a very good course on this hyperparameters choosing and tuning and optimization in Coursera, and I would definitely put a link in the description, so you should definitely take this course, because these are very, very important when you are going for a interview, and you should be very familiar with how you're going to set up all these values. All right, I hope you have got something new today, and keep checking our other playlist, and that might help you a lot. All the best for your preparation for a data science interview. Take care.